These are our gravity notes, and so you should have a sheet that looks like this for Cornell notes. If not, you can set up your own Cornell notes. That's always an option. But our topic today is gravity, and our essential question is, how does gravity affect an object's motion? So how does gravity affect an object's motion? So I'm going to pull up our notes presentation, and we're going to go through this together, and you can pause this video, you can look back at it, you can watch each slide again and again if you would like to. But the very first thing that we're going to start off is with what is gravity. And gravity is a force. Gravity is an invisible force that you can't see, but it's a force that pulls all objects together. So it pulls all objects together, and I have all objects underlined because we don't normally think about all objects like your book bag being pulled towards your notebook or your chair being pulled towards your table, because we don't see that happening. The reason we don't see those things happening is because we are under one gravitational pull, 1G, downward towards Earth. And that gravitational pull is so strong that we don't see stuff actually pulling towards each other, or having any motion towards each other, because our gravitational pull is pulling us downward with so much force. Our Earth is very, very massive and has a lot of gravitational pull. And we call that, again, we call that 1G, that we're always under all the time, one gravitational pull towards Earth. All right, so what is the universal law of gravitation? And this is a law that was also written by Sir Isaac Newton. He had a lot of laws. He had the Newton's 3 laws of motion, and he had this law. The fable goes, or the story goes, he was sitting under an apple tree and an apple fell, and he thought, what caused it to do that? And so he started studying gravity and studying the motion, but he determined that there's something pulling that apple down out of that tree. I mean, there had to have been a force that pulled that apple down, because why didn't it go forward or backward or sideways or up? So he said there had to be a force there. And so he determined that the force of gravity acts between all objects in the universe without exception. All objects exert a gravitational pull upon each other. Again, we talked about on Earth, really the only gravitational pull we see is our pull downward towards Earth, because we are constantly fighting against gravity most of the time. If you want to climb a tree, you're fighting against gravity. If you're climbing Everest, you're fighting against gravity. If you are walking up a hill, you're fighting against gravity. If you're flying a plane, you're fighting against gravity. So we always are under that 1G. But if you get outside of the Earth's atmosphere, there's also gravity. There's gravity all throughout our universe. And so all of those objects, all of those planets and stars and galaxies and comets and meteors and whatnots that are out there that are considered objects or mass, they have a gravitational pull. So what two things affect the amount of gravity exerted between two objects? So let's come back down and let's just talk about two objects and isolate those two things. And the two things that make the difference there in the gravitational pull is mass and distance. So the mass of the objects is a really big deal, and the distance between those two objects are a really big deal. Well, how do those affect each other? Well, the first thing is, let's look at mass. If it has a lot of mass, things like planets and stars and our sun is just a star, it's just an average sized star, they have a lot of mass, so they have a lot of gravitational pull. If you have two things like an apple and a lemon, not much mass, not much gravitational pull. If the distance between things changes, that also changes the gravitational pull. So objects that are closer together have more gravitational pull. Objects that are further apart have less gravitational pull. So let's take this, the closer together and the more gravitational pull, and let's talk about our solar system. Our sun, talk about kind of these two things together, mass and distance. Our sun is the most massive thing in our solar system. So therefore, all the planets in our solar system and objects and whatnot are going to orbit the sun because it has the most mass. So it's pulling on us with its gravity. We and our planets have a lot of mass as well, so we're pulling back. It's almost like that tug of war we watched in our PhET simulations. And so we're pulling back, and so it gets to a point where they're balanced, and then what you end up with there is an orbit. It's pulling on you, you're pulling on it, so the sun's pulling on the earth is pulling back on the sun, and it creates an orbit. Same thing with the moon, the same reason the moon doesn't come crashing down to earth. It has a lot of mass. It has about 1/6 the mass of the Earth. And so it pulls on the Earth, and the Earth pulls on it. The Earth has more mass, and so the moon is going to orbit the Earth. So let's talk about this a little bit more. So the reason we orbit the sun is because we're closer to the sun than we are to any other star in our galaxy. Our sun is the only star in our solar system. You think about, oh, well, I see stars in the night sky, but guess what? Those stars are not in our solar system. They're looking outside of our solar system, which is a pretty cool thing if you think about it. And every single one of those stars out there may have just as much, if not more, mass than our sun. But the reason that we don't orbit them is because we're so far away from them. So distance and mass are the two things that play a role in when two objects and how they exert gravity on each other. So then we're going to talk about weight. And you think, well, what's weight? And how does that have to do with gravity? We're just talking about gravity. Well, weight is really a measure of gravitational force. It measures the gravitational pull on an object. And it's not the same thing as mass. A lot of times we talk about mass and weight being the same thing because on Earth they kind of are, but they really aren't. So that's kind of weird to say, isn't it? But the weight can change if gravitational pull changes. All right, so if I travel to the moon, my weight's going to change. If I travel to Mars, my weight is going to change. And it's measured in newtons. I know we measure weight. You say, well, I measure my weight in pounds. But that's our customary system. Weight is really measured in newtons because it is measuring force. It's measuring a force of gravity. So you think, well, okay, let's talk about weight and mass. How are they different then? What's the big difference? And remember, mass, you learned this definition when you were young. Mass is the amount of matter in an object. So all those things, all those molecules, all those atoms that make up objects, that's where the mass comes from. And the weight is the amount of force pulling that object downward, on our case, towards Earth, right? And so, again, if the gravitational pull changes, the mass will stay the same and the weight will change. So the mass will stay the same and the weight will change. So again, if we were to load up and take a field trip to the moon, remember the moon has 1/6 the gravitational pull of Earth. So that means our weight is actually going to change to be 1/6 of what it is on Earth. So you could take your weight and divide it by 6, and that's what you'd actually weigh on the moon. However, all of our mass, all of our bones and blood and our cells and our molecules that make up our body is not going to change. That's not going anywhere. That's not, you're not getting smaller. You're not shrinking. You're not losing bone mass. You're not losing anything. Your mass stays the same. So the mass of the objects do not change when the gravitational pull changes, but weight will. So that's the main difference in those two. Now, let's talk about free fall. Well, what if I am accelerating, or I have an object that's accelerating towards Earth, and it's known to be in free fall? And free fall is when the only force on an object is gravity, by definition. When this skydiver we see here, we say, oh, well, he's in free fall. Or you ride the ride at Six Flags or Wild Adventures called the free fall, just drops you down. Technically, in science terms, the only force needs to be on an object is gravity. And we know that this skydiver has an upward force. If you're thinking real hard, he has an upward force of air resistance. And we'll talk about air resistance in just a minute. But we call this guy in free fall, but technically things are in free fall only when they have gravitational pull. And that's the only force acting upon it. But if you're near Earth, one interesting thing about free fall is everything accelerates at the same rate regardless of the mass that it has. Everything accelerates. So that means it gets faster and faster and faster towards Earth at the same rate regardless of the mass. So it doesn't matter how much something weighs if it's falling towards Earth. It's going to accelerate at the same rate, okay, regardless of its mass. So let's talk about this a little bit further. So what is this rate of acceleration due to gravity towards Earth? So near Earth, any object accelerates at a rate of 9.8 meters per second squared, regardless of mass. So it doesn't matter how much it weighs, how much mass it has, all right? So we see our elephant and our mouse down here. And our elephant obviously has more mass than our mouse, but they are going to accelerate towards Earth at the same rate, and that same rate is the 9.8 meters per second squared, until those objects reach terminal velocity. Terminal velocity is going to be the fastest speed it can go, and we'll talk about that in just a second. But this rate is the same for the elephant and for the mouse. So let's talk about terminal velocity. What is that? That's the greatest velocity. So that's the speed and direction, right, that a falling object can reach. Normally, skydivers will reach around 122 miles per hour. It's pretty fast just to be jumping out of a plane and going 122 miles per hour. That's kind of normal. If you pull your arms and legs in like this guy right here, he's kind of laid out there a little bit. He has his arms wide, his legs wide, but if you were to be able to pull in and kind of cut through that air a little bit, you could potentially reach up to about 200 miles per hour. Now, I have a video of this guy. His name was Felix Baumgartner, and he actually jumped from the edge of the atmosphere. It's pretty cool. It happened a couple years ago, 2013 maybe, a few years ago, and it was a thing sponsored by Red Bull. It was an event sponsored by Red Bull. And they actually took him to the upper atmosphere, almost to outer space, what we would probably consider outer space, and he jumps. And there's a video of it back on your it's not a YouTube video, but it's on your Google Classroom. So I encourage you to watch that. And this guy, he reached a speed of 843.6 miles per hour, was world record. But the reason he could reach this speed is because he was so far out that there was very, very few air particles. He actually had to wear an astronaut suit to be able to survive that, because there's no oxygen and oxygen masks and all kinds of things. But you can watch that, and it's pretty neat to see. But the reason he got so fast is because there's no air resistance pushing up. So let's talk about that air resistance for a little bit. Air resistance is what is a type of fluid friction, and it opposes and slows motion, which in the case of a skydiver, that's what you hope happens with your parachute. You open your parachute, it creates friction, it creates drag, it opposes and slows the motion down so that you can safely hit the earth. Now, air resistance is not the same for all objects. For example, this leaf and this acorn that I have down here, this leaf is going to kind of float to the ground because air gets kind of trapped up underneath it, and so it pushes up, and so the leaf is going to float downward. Unlike the acorn, so the acorn is a little more aerodynamic in its shape, and so it's going to cut right through, and it's just going to kind of drop down. So when you think about these two things accelerating towards Earth, you're like, well, they don't accelerate at 9.8 meters per second squared. That's not true. But the reason is because of air resistance. Okay, so let's go back to that 9.8 really quickly. This 9.8 right here, this is a constant. Okay, 9.8 meters per second squared. Anytime you have a problem and they say, oh, something's falling towards Earth, and they don't give you a number, they're talking about this rate of acceleration right here, this 9.8 meters per second squared. Okay, so don't let that confuse you. Back to air resistance now, talking about this leaf and this acorn falling. This air resistance sometimes is called drag. So if you have a parachute or if you have an airplane, maybe this air resistance going through would create drag. On the bicycle, we talked about making stuff faster. You know, if you can cut down the air resistance, you can increase your speed tremendously on moving objects because it really slows you down. It creates drag. All right, now we're going to talk about projectile. So we've got projectile motion, and even if you shoot something out of like a cannon right here, we've got this cannonball being shot, it's still going to have a curved path downward back towards Earth, and the reason is because gravity is pulling it downward, but you've projected it forward. And you can also, there's another thing you can do is just drop it. If you drop the cannon out of where this is being shot, the cannon's going to drop. The cannonball's going to drop straight down, again, affected by gravity. The weird thing about projectile motion, and projectile just means it's thrown or projected with a force, is that a projectile will hit the ground at the same time that a dropped object hits the ground if, this is a big if right here, because you think about that, that's like, no way, if I throw something and drop something, it shouldn't hit the ground at the same time. Logic just says that. There's two ifs here. If they are dropped or thrown from the same height and you're in the absence or you don't have any air resistance. So those are two big things that could change the rate at which a projectile falls to the ground and the rate at which something is dropped and hits the ground. So But if you have them from the same height and you have no air resistance, they actually will hit the ground at the same time, which is still really hard to believe. And so what you need to do is I have a Mythbusters little snippet clip on your Google Classroom. So I want you to go watch that because they can really slow it down and do the still frame and slow motion photography. And you can see where they're going to shoot a bullet and they're going to drop a bullet, and they're going to watch those through videos and slow it down. So you're going to see that they actually hit the ground at the same time. It's pretty neat. It's kind of like seeing is believing. So that's experimentation. All right, and let's talk about projectile motion and then gravity and what that can do for us. So knowing this kind of stuff and knowing this technology, we can put satellites into orbit, which really makes our whole livelihood possible now. You think about everything has Wi-Fi. You know, we can Google anything, and you know, our cell phones, we can call China if we wanted to and get somebody and talk to them on the other end. And the reason we have all this communication and things is because we have satellites. The reason we have, you know, cable and we have long distance communications because we can control a lot of this, which is amazing. So we have satellites that orbit the Earth, and different satellites orbit at different altitudes. And so these things have to be launched into orbit, and they have to stay there. They have to stay there so that they can beam signals, you know, electromagnetic signals, radiation to and from places. So a satellite orbits the Earth in a nearly circular path. So again, a satellite can be anything from International Space Station to the moon to a man-made satellite for AT&T or Verizon or whatever. So the motion of the satellite is forward because they're launched off of the Earth, right? We have to projectile them into space, and so they're launched, and then they're going to be launched out with a forward kind of motion. But gravity is also going to push them downward. So you can see this plane or this rocket ship is flying, but he's also being pulled downward. So what happens is you have a combination of forces. The forward motion added to the downward pull motion creates a curved path known as a free fall orbit. Okay, so the reason that this stays is because the projectile motion, this forward motion, wants to stay the same, because an object in motion wants to stay in motion. That's inertia, and that's the reason it's going to stay in orbit. And the downward force, they become balanced. So the forward movement and the downward gravitational pull are balanced. And so when you do that, you get a zero net force acting on an object, on the satellite. And so the zero net force means it's going to continue doing what it's doing. There's not going to be any change to its motion. Just like yesterday, we were looking at on the PhET simulation. When you have zero net force, the thing wasn't moving. Well, that's exactly what it's supposed to do. Zero net force is not going to move an object. So inertia will keep this orbit constant. So those satellites that are out there, they are not being fueled by gasoline or anything that's propelling them forward. They're not constantly driving a motor around space. They're just in free fall orbit. They're just there, which is pretty spectacular if you really think about the math and all of the technology and all of the things that had to lead to that point to get where we are today. And so just understanding the fundamentals of that is really eye-opening and really interesting. So that brings us to the end of our notes, and I will give you a comprehension check that looks like that. But before we do the comprehension check that looks like that, let's go back to our lab report. Not our lab report, our Cornell notes on gravity notes, okay? And let's look at the back page. Yours is on the back, yours is front and back. At the very bottom, it asks you for your summary, and just like I normally do, I ask you to summarize your EQ. And our EQ says about how gravity affects an object's motion. So you're going to use these terms: acceleration, terminal velocity, projectile, weight, 9.8 meters per second squared. That is a term I want you to use. Orbit, mass, and distance. I think there's 1, 2, 3, 4, 5, 6, 7, 8, 9 terms that you need to use in your summary. And I will read those. So when you get finished with your summary, when you get finished with your summary, I want you to turn it in to me or raise your hand, and I'll read it and check it off like I normally do, and then I'll give you your comprehension check questions, and we'll be able to go over those as well. So when you get finished with this, just let me know, and I will help you get that checked off and get your points in the grade book. All right.